Good afternoon. We're going to carry on with our second chapter. And so this chapter was about work and heat. Last Monday, we covered up to this point, up to page 2.9. And today we're going to finish off this chapter. Before we start, are there any questions from last week? Anything you want to raise? Okay. So, this topic, polytropic processes, I would say this is probably one of the most important. This page itself is probably one of the most important pages of your whole booklet. It talks about a process which you'll come across a lot, and it's called polytropic process. This is a process which relates pressure to volume, and it identifies 4 different categories of processes. And they're all categorized under the brand of polytropic process. I really want you to understand this diagram. I want you to understand these 4 curves on this diagram and really memorize it. Okay? So I want you to memorize this diagram, be able to reproduce that, and understand these 4 processes. So let's just go through those. What we are saying really is that there is a generic equation which relates pressure to volume, and that is P times V to the power of n. Now, the value of n plays a critical role here. Whatever n is will identify the nature of that process. For now, let's just assume that n can take 4 different values, or 4 different range of values, if you like. Before we start, let's just make sure that you still remember that this equation and this equation are essentially the same. The only difference being that this equation has been, if you divide both sides of this equation by mass, then you end up with this equation. The only difference being that here we've got volume. This is a specific volume. That's the only difference. And again, remember that V over M is the specific volume. Now, and of course, if it's to the power of n, then that has to be m to the power of n equals v. Now, what we need to be doing now is we're going to be talking about this n. This n is really important. This is what we call polytropic index of expansion or a compression, or simply we're just going to call this polytropic index. So, mathematically, if you think about the value of n, this makes sense. Now we've got PV diagram. If you set n to 0, then, of course, you're going to have a constant pressure. So V is going to be 0, it's going to be 1, therefore you're going to have P equals a constant. If you have n to the power of infinity, then you're going to have a constant volume type of process. So pressure is not going to change. Essentially, pressure is going to change, the volume is not going to change. So you have this completely vertical line, which means the only difference is really in terms of pressure. Volume is going to stay constant. In between, you could have n equal to 1, or actually it could be n bigger than 1, all the way to infinity. So of course there are loads of, you can draw millions of curves here, but these are essentially the boundaries. These are the limits on n. Each of these 4 processes will produce a different type of process, and this is what we've got here. This list is critical for us. Let's just go through that. If you go from point 1 to point 3, of course you have a constant volume. That process is called isochoric. Isochoric means that choric essentially is, in this case, is volume, and therefore it means that the volume is going to stay the same. So remember that name. this line is isochoric. On the other hand, if you think about process 1 to 2, when n is equal to 0, and you have a constant pressure, that is called isobaric. Now, these two are actually less common. When it comes to actual engineering applications, these two are not as common as the next two, which I'm going to explain now. What if n is equal to 1? That is process 1 to 4, for example. And in that case, you end up with this equation, which a lot of you will actually may recognize. That's what we use for in ideal gas law and lots of things that we're going to come across this a lot in the future. For now, let's just assume that if n equals to 1, then this process is actually, this happens at a constant temperature, and therefore that process is called isothermal. There is one special case when n is equal to a certain value, this constant called gamma. So this is gamma. And gamma actually, I'm not sure if you've covered that in the past, but it's actually a ratio of Cp to Cv. And we'll come across Cp and Cv. I'm not going to talk about those. What you need to know now is just gamma is the value of Cp over Cv. And when that is the case, then you have a very special case called isentropic or isentropic process. In all these four processes which I explained, something stays constant. And I think what you need to do, you need to make sure that you understand, for example, in isobaric, what is that quantity which stays constant? In isobaric, what's that quantity? And so on and so forth. So I think the only thing which might be a bit confusing is probably isochoric, because isobaric, of course, comes from the term bar, and that's the unit for pressure, so you can relate that to pressure. Isothermal, that means temperature is constant. Isentropic means entropy is constant. And the only thing which you may have to remember really is just is isochoric. Now, this value of gamma, which we're going to come back to this later on, for example, for air, is normally 1.4 at a constant temperature, because when the temperature varies, then that constant varies as well. But just to give you an idea, that's the sort of value that we normally work with as far as, whenever you have air in your system. So, and as I mentioned, these two are very common. Now, let's just move on now and think about, I want to start deriving one equation, or actually a series of equations, which are the first equations in your booklet. So if you look at the formula sheet at the first page of your formula sheet, your booklet, that's the data sheet. We're going to be looking at these four equations here. These are essentially the equations to find work for those four processes. Do you have a question? N is negative, yes. Yeah. Actually, that's a very good question. N could be negative, and if N is negative, actually, when N is negative, graphically, mathematically, the curve looks like something like this, for example, right? We're not going to cover that because under the second law of thermodynamics, processes in which n is less than 0 and it's negative, they're not really practical. But we're not going to cover that for now. There's one example later on which uses actually n equals minus 1 over 3, but that we're not going to really look at the physical meaning of that. It's more about the practice of using equations. But because it's not that common, we haven't included that in this figure. But in reality, yes, you will have values of n actually negative. You could have values of n, in this curve, for example, is roughly maybe n equal to -2. But anyway, that's just beyond the scope of this unit for now. Yeah. Okay, so as I was saying, we are now deriving these equations that you can see here in your formula sheet. So, if you have this PV diagram and you have a process in which you're moving from point 1 to point 2, this is the situation where, for example, n could be equal to 1, or it's actually bigger than 1. It's one of those, it's either this or this. Doesn't really matter for now. So, what you see here is that as you move from point 1 to point 2, obviously specific volume is increasing, right? So that is actually increasing. So dV, change in the specific volume, will be bigger than 0. And of course, pressure has to be bigger than 0 as well, because you can see there's no negative pressure here. Pressure is a quantity, is positive, and therefore that equation, or the change of work, should be positive as well. So you're doing some useful work here. Always remember that the area under the curve in the PV diagram gives you the amount of work that you've done. So if you integrate this curve, that area, which is shaded here, that will give you how much work you've done. And this is actually what we're going to be using in order to derive an equation for work for this specific equation. Now, let's just start again with the fact that PV to the power of n equals to a constant. And I can rearrange this equation naturally. And I can write that P is equal to this constant divided by V to the power of n. And what I can do, I can use this definition of P in my work equation. Now this bit is simple. It's just a bit of mathematical modification of the equation in order to allow us to derive the final equation. So what we're doing now here is that it's not very handy to have this fraction in this equation. So what I'm going to do is, the first step is to bring this to the numerator and change the sign of the power to -n. That's fine. From here to here, what I'm doing really, I'm trying to change the differential. So the differential here is dV. Here is dV to the power of 1 minus n. The reason why I've done that, you'll see actually later on why that is useful. I want to change my differential because then it allows me to derive this equation in a sort of an easier and faster way. If you struggle to understand how that is done, I mean, that's just very basic mathematics, but if you think about, for example, a generic equation, integral, x to the power of 5, and you want to integrate this with respect to x, that's naturally 1 over 6 x6 plus a constant. Also, that is equal to the integral of 1 over 6 dx to the power of 6. So, if you think about moving from here to here, these are exactly the same. The only difference being that now you've changed the differential in this integral. So instead of doing it with respect to dx, now it's with respect to dx to the power of 6. And you can do that, and that's exactly what we've done in here. So, focusing on that elemental work, what I mean by elemental work is this bit. where we normally want to derive something, we look at a small section of that area. And that allows us to derive an equation that is useful. So far, what we've done this change, and as I mentioned, I've explained so far how we got to this point by changing the differential in the integral. And when you want to do this integration, then simply this is c over 1 minus n, that's a constant, and then that comes out of the integral, and you've got the two limits of v2 and v1. These are the volumes at point 1 and point 2, and that's how you can evaluate this integral for that element of work. So let's just remind ourselves that actually, so P1 V1n is equal to constant, that we know. That, of course, must be equal to P2 V2 to the power of n as well. And, of course, you can use the same subscript for 3, 4, 5, etc. So if I now want to go from here to here, so essentially you want to insert these constants into the equation here. So you need to replace v with v2 and then with v1. This is what you get. So that comes from here. And of course, by observing the fact that c it can actually be written by p1 v1 to the power of n or p2 v2 to the power of n as well. So here, this and this, these are my c. Now, if I simplify this equation, then you end up with this equation. Now, this is for the case when n is actually bigger than 1. So it's actually more difficult. When n is bigger than 1, it's slightly more difficult. I'm going to be looking at the case where n is in fact equal to 1, and just see how my simple equation of w will be simplified for this specific case. So let's just make sure we understand that when n is equal to 1, then because we have PV is equal to a constant, therefore pressure can be written as constant over the specific volume. And similar to what we had here, the only difference now is that obviously n is 1. And in order to find W12, all you need to do is write or replace P with C over V in that equation. And you know when you want to do the integration of something, dV, for example, by V, you've got to use the natural logarithm. That's ln V2 over V1. And simply by noting the two limits here, that is simplified to that equation. And because you can change P1 V1 to P2 V2, these are the two equations that you can write for this specific case. Now, if you look at that equation here, I'll just highlight it, and that equation here, these are exactly the sort of equations that you get in your formula sheet. Just going to show you. So when n is equal to 1, that's what you get. And when n is bigger than 1, then that's the equation that you get. It's slightly different in the way that it's written, but again, I encourage you to look at this format, because that's what you're going to be given in the exam, and that's what you're going to be using more often when you're doing the tutorial sheets. Therefore, it's good to familiarize yourself with the notations, with the way this is written, etc. If I do this example, I think the application of this equation becomes clearer, I think. So we've got a process. In this process, again, we've got a spherical balloon which inflates. And this is a quasi-static process. So everything is done in a very slow pace because of the reasons that I mentioned. Because if you do it too fast, then you are introducing uncertainty, such as turbulence, pressure waves, etc. Therefore, you can't use these equations there for now. So what do we have? The initial radius is 0.1 meters. So R1 is 0.1 meters. And R2 is 0.2. During this inflation process, the pressure behaves polytropically, as we know, according to this equation. And N, in this case, is equal to minus 1/3. The volume of the sphere, we know, is given by this equation. Again, that's a generic equation for the volume for a sphere. And R is the radius. The other piece of information we know is that the initial pressure is 1 bar. What do we have to find out? We want to find out what is the work done by the system. Looking at the equation from the formula sheet, this is the formula which we want to be using. This is the one that we just derived in here earlier. That is this equation. Now, if you think about this equation, we know the value of N. We know we can work out the value of V1 and V2. We have P1. The only thing which is missing actually is P2. So I need to find out what P2 is, and then that would give me the value of work. So, of course, note that V1 and V2 are defined, obviously are a function of R1 and R2. Then the first thing I'm going to do is I'm going to relate P and V using my polytropic equation. This equation here, or this simplification, you might struggle to understand how, I mean, some of you might be simple, but I'm just going to explain and show you the steps, how we go from the the polytropic process to this simplification. So we have P1, V1 to the power of minus 1/3. Of course, that is P2, V2 minus 1/3. I'm after P2, so I want to rearrange this equation in the form of P2. So that is naturally P1, V1 over V2 to the power of minus 1/3. Now, I want to make it even easier because I know the value of R, and therefore I want to replace V with R if I can. So that is actually P1, R1, R2, both to the power of 3, and the whole thing is to the power of minus 1/3. Note that 4/3 pi has been cancelled on both sides, in the numerator and the denominator, and you're left with R to the power of 3. And, of course, you can simplify this even further, and that is P1, R2, R1. I've inversed this fraction because I've got a negative power here. And that's how you get that simple equation. All you need to do now is to insert P, which is 1, 0.2 and 0.1 for the radius, and you get 2 bar as P2. Now the next step is just go back to the original equation that we know for W and start inserting the values in there. And that is quite simple. What you find out is that, again, V can be replaced by 4 over 3 times pi times R. And actually, this and this will be cancelled. And you're left with pi, P2, R2, and so on. When you start inserting the numbers, you get the value of work, which is 4.7 kilojoules. It is important to use the pressure in Pascal and not bar when it comes to... I think it's a good practice in general to work with Pascal instead of bar, because when you have bar, then when it comes to SI units such as joules, then you're going to struggle in terms of that 10 to the power of 5 factor. So pay attention to that. And of course, this 100 here is as a result of the fact that 1 bar is equal to 10 to the power of 5. And because we have here kilojoules, that does take that into account, and therefore this is 100 instead of 10 to the power of 5. That's just a note for you to remember where this 100 comes from. Any questions? Yeah? So this is when n is not equal to 1, yes. So going back to the question that one of you asked, actually. So even though this question, n is this strange number of minus 1 over 3, I think would have been better if, for example, in this case, n was equal to 1.4 or 1.2, something like that. The whole procedure would have been exactly the same. The values would have been slightly different. But, yes, so that equation, this equation here, is for situations when n is not equal to 1. A note of, following up that question, if you think that this question is generic, and therefore I can, this one. If you think this equation is generic, and therefore I can use it in situations where n is equal to 1 as well, then you end up with having this equation in the denominator, you're going to have 1 minus 1, and that just doesn't make sense. Therefore, this equation is strictly for situations when n is bigger than 1, or is actually not equal to 1. So, next page. Is work a property? We know by now, no, it's not a property. What this section does really, it sort of shows you why is it not a property. So I said that, for example, the internal energy is, U is a property, but W and Q, which represent work and heat, are not properties. And we're going to see why that's the case. So, again, coming back to this PV diagram, I've got the starting point, or state point 1 and a state point 2. You would agree that I could move from point 1 to point 2 via this curve, which actually represents a polytropic process, as we've seen. You could also argue that if I don't want to follow this PV to the power of n, I could go with isobaric, isochoric, and isobaric process as well. So 2 vertical and horizontal lines, and it still would take you from point 1 to point 2. And the question really is, both assumptions are valid. Both routes and curves are valid. Let's just make this, for example, red. So you know this is one route. And let's just make this one blue. I'm going to call the blue route, which is the polytropic process essentially, let's just call this W12. So when you're moving along the path 1, then let's just call this W12. When I'm moving via the red route, or path 2 and 3, then let's just call this W tilde 12, just to differentiate that from the first one. And now let's start looking at the equations that we derived and see where we end up. The first one is simple. When I have the first root, we just derived an equation for that, which was this one. So W12 is equal to this equation. If I want to follow paths 2 and 3, then of course I will have to apply, I will have to look at the equation for work under those two assumptions. So this and this. The first one is the Isochoric process, and this one is the Isobaric process. But the equation actually is the same. We use the W equation, which is the integral of P dV. That's the most generic equation for work that we've been starting from ever since we introduced work. Now, that is quite obvious actually, that when you have path 2, along path 2, when you have your volume actually is constant and it's not changing, then dV has to be equal to 0, which effectively that means that this term will be 0. And if you just look at this equation now, that just means that P is constant, of course, so this integral, I can take P out, and then my volume will change from V2 and VA. I've got two values here, V2 and VA, as you can see here on this curve. Therefore, my W tilde 12, which I defined, is actually will be equal to P2 V2 minus V1. Note that VA and V1 are the same, and therefore I could just replace one with another one. Because VA and V1 are exactly the same. They're both equal to this value here. Now, naturally, what happens is that this and this, which were W12 and W tilde 12, of course, are not the same. They're not equal to each other. And what does that tell us? Do you remember the definition of property in the first lecture? I said property is path independent. So let's just remind ourselves. A property is path independent. Now, certainly in the case of work, that's not the case, because you've seen now that if you go via path 1, you will get a different equation for velocity, and different value, in fact. And if you go via path 2 and path 3, then you get a different one. As a result of that, that is a proof, that's the best proof that you can show why work is not a property. Now, we've been talking about work for the past 2 lectures. This is where we start with the heat. Heat is as important as the work when it comes to the first law. And there are lots of similarities between the two. But of course, the physical definition of heat is quite different. Now, this was the example of the work that we looked at. You know, you have, for example, a system, and if this system expands, which in this case, for example, is the air inside the cylinder, if it expands, then it would lift this weight. And the work done by the system in this case will result in potential energy in the form of weight, in the form of this movement of the weight. So work was a transfer of energy from one form to another. In this case, you've got the energy moves from the system to the surrounding. And in fact, heat is exactly the same thing, but the only difference between work and heat is what is causing that movement or the transfer of energy. In work, it's the actual force. You have to have some sort of force, mechanical force, in order to make that change. In heat, it's actually simple. It's just the temperature difference. All you need to have in order to produce heat is to have temperature difference. So temperature difference is really the cause of heat. And therefore, really, the difference between work and heat is really just, it comes from the second law of thermodynamics, which we'll come back to this later. But as far as you're concerned now, if you have some sort of physical force, that will produce some work. If you have some temperature difference, that will produce some heat. The units are exactly the same, joules in both cases, which it actually must be, because if you think about the internal energy equation, the first law, on the right-hand side you've got Q and W, and of course they must have the same units, otherwise you just can't have the same equation. So what else? This is the bit which I talked about, temperature difference and force, which is the main difference between work and heat. And of course, the same assumption goes with the heat as well. The quasi-static, what I mentioned in the mechanical force, in the work, which was in the displacement work, which was moving the piston in a cylinder, for example. You can't just do it very quickly, because if you do it very quickly, you will introduce that turbulence and pressure wave inside the cylinder. It has to be done in a very slow pace. The same applies to temperature. Again, that doesn't mean that we can't solve any problem which is not quasi-static. That just means that as far as this unit is concerned, and some of the fundamentals of thermodynamics, you've got to make this assumption, otherwise you won't be able to start from the basic equations that are fundamental to the thermodynamics. So for now, just bear with us and assume that this is the main assumption, and then we will introduce later on some real losses which would change this assumption. And the systems that we consider in this module will be, essentially on the whole, will be limited to a single well-defined temperature. And that's actually how we implement this quasi-static assumption, by having a single well-defined temperature in our problems. Something to note is that, of course, you've heard about heat transfer, and it's a very important topic. You've got heat transfer next year, and in the third year and the fourth year, in fact. Heat transfer, the mode of heat transfer, is not really... The reason why the thermodynamics and heat transfer are two different subjects is because heat is more about the physical side and what happens when you have a temperature difference. Heat transfer is actually more about the process of what happens when you have a temperature difference, and what are the different modes of that change of energy. So in Appendix 1, what you'll find is the types of, or the modes of heat transfer: conduction, convection, radiation. That's just, again, I think for your own information, we're not going to touch on, we're not going to do anything on heat transfer really in this year. But I just want to make clear that there are some differences. While they stem from the same principle, they will actually branch out into two different subjects. So here we don't care about what is the mode of heat transfer, whether it's conduction, convection, or radiation. We don't care about that. As far as thermodynamics is concerned, we care about that temperature difference that exists in the system. Now, there are 6 simple statements here, which summarizes what we've been saying about the heat. Let's just go through them so that, just to make sure that you're all familiar with that. Heat interactions are associated with energy transfer. Heat interactions are transitory phenomena. Heat is energy transmitted across a boundary. We've covered all those. Heat is not a quantity, very similar to work. If 2 points at different temperatures are brought into contact, then heat is the energy transferred. This is actually based on the zeroth law that we've explained. And heat is not a property. If I just quickly move on to, got lots to cover, so I need to go a bit quicker on this. Here is just a simple example about, it's more about a historic understanding of what heat used to be conceived in terms of what people thought heat is. It was believed that it's a sort of an indestructible fluid which actually is contained within a body. For example, if you have a duster and you start moving it on a surface, it generates heat, and it was believed that there's some mysterious type of force or energy inside each object, which was called, for example, caloric. And obviously that we know is not the case. It's just a matter of transfer of energy. What I want to talk about next is actually about sign convention. So we had a sign convention for work, negative, positive, etc. And we spent a lot of time on that. And it was distressing for a lot of you. Now, here we have a new sign convention for the heat. So heat into a body is positive. Heat out of a body is negative. So if this is the body, if the heat is going out, then it's negative. If the heat is coming in, it's actually positive. What that means is that actually, if you realize, this is opposite to the one that we use for work. Now, what does that mean for you? Let's just draw a simple diagram. This is what it exactly means, because you need to think about, so you can't just look at that mathematically. You can't just think about the fact that, well, the work by the system was positive, therefore the energy, or the heat in this case, is going to be positive. No. What you need to think about actually here is about losing or gaining energy. So if, in this case, for example, when you are doing some work, when we had it previously, when you do some useful work, then we said that the work is negative. The work is positive. And then what it meant is actually that you've lost some energy. What I mean by the opposite sign convention is that when it comes to heat, when you gain energy, this is actually something which is seen as positive. And in that sense, there's an opposite convention. But again, when you start looking at some examples, it makes more sense. Let's just do one very simple example here. We have a cylinder, and it's enclosed by a piston, and is maintained at a constant pressure of 5 bar. So here we have 5 bar. That's the pressure. At time 1, this is what we have. And at time 2, we have an expansion. What happens is that actually during this time, we have some heat going into the cylinder. Maybe you're just heating up the cylinder with a candle or with a fire or something. That's just how you could introduce heat into this. 12.5 kilojoules of heat is transferred to the cylinder, but the internal energy is unchanged. And that's an important assumption here. So what we want to find is what is the change of volume in this case as a result of introducing that heat into the cylinder. I'm going to start with the first law equation, where you had the internal energy. If you are confused about the right-hand side, which is E in this case, as opposed to U, in this, as far as this topic and this chapter is concerned, it doesn't really make a difference. We come back to the difference between U and E. E is more generic. U is the intrinsic internal energy, but E is actually more than that. But just for now, let's just assume that the right-hand side doesn't really matter if it's E or U. on the left-hand side, we've got heat minus W. So let's just see how that works. So, because the right-hand side of the equation is 0, because we know that there's no change of internal energy, I can simply move the work from the left-hand side to the right-hand side and say Q is equal to W. I don't have any equation for the Q for now, but what I know is that because this is a displaced work, or displacement work, then this equation applies here for work. The integral of P dV, we've seen that a lot of times. So let's start with that. We know that the pressure is going to be constant. The problem says that pressure is maintained at 5 bar, therefore P can come out, and the integral will be simplified to V2 minus V1. And in fact, this is actually what we want to find. What is the change in the volume? We know what Q is, because that is the amount of heat which was added to the cylinder. And I can relate that, and also we know what the pressure is. So by rearranging this equation, then you can actually see the change of volume by dividing Q by the pressure. So this is how much your volume expands when you start adding this amount of heat into the cylinder. The rest of this page really is about calories. It's just as a unit. We don't use calories in this module a lot. It's just, but because it's a common unit, I think it's just useful for you to know that 1 calorie is 4.1868 joules. And I think the other thing I want you to just know as a general knowledge is just a definition of 1 calorie, what that signifies. This table, it just gives you some overview of the scale of temperature and heat. I'm not interested in that really. Again, it's just for your own understanding. The last page, which I want to cover quickly, is again another analogy between heat and work. It's very simple. By the way, the difference between this page and your page is that you don't have this. But then this is actually, I've just copied and pasted from the appendix, just to make it easier. But that figure is actually in your appendix, so don't worry. So the first thing I'm going to say is that very similar to work where we had PV diagram, you could have the same 2-property rule, 2 independent properties, and that would allow you to plot this diagram which would represent your heat process. So like the cylinder example, just the example that we just did, you could move from point 1 to point 2 by adding some heat into your process. Very easily that can be plotted in this diagram. Something important is actually, it's not only the case that you either have to have work or heat in this diagram. Actually, it's more common to have some sort of both and a combination of work and heat in the process. And this figure actually represents that. You've got this piston and cylinder. If you start applying force to the piston, of course the pressure and temperature inside will rise. You can actually do exactly the same thing by heating up the air inside the cylinder. So physically you've done exactly the same thing, but first time it was using a mechanical work. Second time, it was using the addition of heat. What does that mean for us? You could actually move from point 1 to point 2 by adding some heat. You could actually then move back to point 1 by maybe doing some mechanical work. If I'm heating this up, and this cylinder, this piston is actually moving this direction, and it's doing some useful work here, by maybe pressing something or doing some sort of useful work, then actually this is what I've done. I've added heat and I've taken some work out of it. And the last diagram really just shows that this could be a cyclic process which means this cycle could be repeated for thousands and millions of times, and this is what we have in cycles such as power plants, refrigeration, name it. I mean, even IC, diesel engines, internal combustion engines, in all of those, because they go through a cycle, they have one sort of, this is obviously an idealized, very easy and random cycle, but this just means that certain amounts of work and heat can go into the cycle, and certain amounts of work and heat can come out of it, and by playing with those factors, you end up with a very nice engineering cycle. And that's what you have every day in those systems that I mentioned. So that's the end of chapter 2 and the work and heat and the first law. In the next, can I just mention about the appendix? So appendix 1 is about the heat transfer modes, which, again, if you like to go through that, it's optional. Appendix 2, though, is actually important. So I want you to go through appendix 2 because that would give you some more insight into what I just explained about the cycles and about work and heat. Okay, so I was going to do a very quick quiz, but there's no time for that. We'll probably do it later on. If you have any questions, please come down and ask me now.